section that you didn't see in regular chem.
What's that one?
The PES, the photoelectron spectroscopy.
Oh, is that what we did?
No.
No.
We did it early on.
Check.
All right, composition of mixtures. When we have things that are combined together, they form a mixture, okay? So the only thing that are pure substances are your compounds and your elements. If it's not a compound or an element, then it's a mixture, okay? And what makes it a mixture versus a compound or an element is mixtures can have variable compositions. So I could have a bucket of salt water and have 5 grains of salt mixed in that water. It would be salt water. I could have a bucket of salt water where I have a cup of salt and a gallon of water. It's still salt water, okay? So mixtures are variable in their composition as opposed to compounds and elements, which are set ratios. So for every compound of water out there, I have 2 hydrogens and 1 oxygen. No matter where I go in the universe, if it's 2 oxygen or 2 hydrogens and 1 oxygen, it's water. Okay, set ratios. No matter where I go in the universe, if I have an atom that has 12 protons in it, I have what? 12 protons. Magnesium. Okay? It doesn't matter if I'm here, on the moon, I'm on Mars, I'm on Jupiter. If it has 12 protons, it's magnesium. Now, if it has the atomic mass of 12, it may be carbon, but it may be an isotope of something else. It's that proton number that determines its identity. That's what you look for to see what it is.
I think magnesium should now be like number 4.
Okay, does that make sense? That is determining its identity. So mixtures, though, their composition is variable. It could, like I said, take you back to that salt water. We're not going back there again. Okay? All right. In mixtures, again, the composition can vary. And we can use stoichiometry, which is your mole ratios. We use the before, change, after tables back in the day. It won't take long to figure it out. It's easy.
Can we do the apple one?
No.
Why?
All right. So elemental analysis can determine the composition of a mixture. It can be qualitative, where we can identify those elements present, or quantitative, where we can identify the amounts of each present. Elemental analysis then is part of that analytical chemistry, okay, which is kind of like when you have beverages or food, they have the analysis of the material on there, the calories, the sodium, the fat, the protein. That's all analytical chemistry, okay? So if you're given the mass, you divide it by the molar mass to give you the moles. Then you use your mole ratio using your BCA table to figure out how many moles you're going to make. And then you multiply that by the molar mass to get the new mass. Okay? So what does this elemental analysis include? A lot of times they're going to do a combustion analysis for this, where they will mix it with, obviously, oxygen from the air. They are going to then burn it and see what comes out of that. They can look then, sorry. There's a couple of different types of spectroscopy out there. There's optical, where the lights pass through a colored solution. We will actually get into that and do that when we get into Unit 3. We will pull out the spectrophotometers, and I will show you guys how to do that. We can look at the mass of the material, and we actually did some of that in chemistry, where you looked at what was remaining in the end, and then you were able to go back and see, okay, my penny should have had this much copper in it. How much should I get for my mass? And then the photoelectron, which is the PES, which is what I was talking about just a couple minutes ago, you look at a graph essentially. So you run it through a machine, you look at the graph that comes out, and it tells you what material was in there. And if you took honors chem last year or the year before, we actually did some of that in there looking at those graphs. They're really easy to do. Just if you don't remember, it'll come back pretty quickly. All right. So here we have our aluminum metal. It's reacting with the oxygen in the air. It is going to form aluminum oxide, and we have an equation here. So the first step we do is we always balance your equation. Correct. Okay. So over here I have, remember, I always look and see where I have even and odds. Okay. And I leave these singletons to the end. So even and odd, we double the odd. So I'm going to put a 2. I'm going to try to put a 2 here. There. I'm going to double that odd oxygen there. Then I'm going to go back over to this side, and I'm going to get these single elements that are not in compounds to balance. So here I have 4 aluminum. Here I have 6 oxygen. 2 times 3 is 6. So I need to put a 3 here. 3 times 2 is 6. So that is balanced out now. All right. They told us that we are, so we balanced the equation. We're going to find out the mass of the oxygen that was in the sample. Okay. Well, we know that we had aluminum and aluminum oxide, a mixture of that. We have our mass here. They're analyzed. The total amount of the aluminum was this much. Okay. So if the aluminum weighed this much, they want to know how much oxygen was in that sample. What do? We subtract. Yep. We're going to take this minus this, and we're going to come out with our oxygen amount, which is 0.59 grams of oxygen. Okay. What is the mass of the aluminum oxide in the mixture? Well, there we're going to have to do a little bit of math. Okay. So we know that we have, for our O2, we know that this is how much oxygen we had to start with, right? Yep. So 4, yeah, we know you're smart, Ben. We get it.
No, I just said party.
Oh, I thought you said I already got it.
No, I said party.
All right. So here's my equation. I'm just rewriting it again to get it down here to make it a little bit easier to work with. Now, I cannot put grams in my BCA table.
So true.
The B stands for before, the C stands for change, and the A stands for after.
We need to go crazy with these numbers.
So I'm going to take this, and I'm going to divide it by what? Not 16. 32. Remember, this is O2, so I've got to take 16 plus 16 to get 32. So I'm going to divide it by 32. So 0.59 divided by 32.
76.
Remember, when you're doing this, you want to have at least 3 significant figures, 3 non-zero numbers in this chart. So 0.675. And that is the moles of oxygen.
0.018. That's not right.
You're right. That is not right. 0.59. I had another digit in there. I didn't clear it out on my calculator. Yeah, I wouldn't. I don't know that I would do that. All right. Here we go. Let's try that again. 0.0184. Better? Sorry. Call me on those things. I will make mistakes all year long. Don't be afraid. All right, now, when we're working with this, if we want to find out what this value is, which is what we're looking for. Yep, we're going to go up into the cloud. And what that means is we're going to take this value and we're going to divide it by this coefficient. So take this divided by 3, and that's what they're talking about, a cloud here. So we're going to take this divided by 3. And that ends up being, and you want at least 3 sig figs here, 615. Okay. And then you're going to take it back down out of the cloud. We reverse the operation. We divided to get here, so we're going to multiply to get here. So times 2 is going to take us to 0.0123. What we've done there is just a mole ratio. For every 3 of these, we have 2 of these. That's all we're doing, is just a mole ratio. You can think of it like that if you need to. For every 3 of these, I have 2 of these. So that's how you would do the math to get that mole ratio to come out right. Now, once you have that, that is in moles. But they didn't want moles. They wanted...
They wanted
mass. Okay, we'll get to mass percent in just a second. They wanted mass for C here. So now I need to do what? Yep, so I can do dimensional analysis, or if you're getting comfortable enough with this, you can just simply multiply it by its mass. So it just depends on where you're at.
That's a lot of stuff to put together. Where's the PDF? 24 plus 82.
Good. Do you see where I got this number from? I took 2 aluminums. So 27 plus 27 is 54. And I took an oxygen, which is 16 plus 16 plus 16. Okay. All right. And maybe it's 102 if you round it, but at any rate. Yeah, it's 102. All right, so 102 times this value here, that's going to give me 1.25 grams of Al2O3. All right, now they wanted to know what is the mass percent of the aluminum oxide in the mixture. So the original mixture was 120.32. No, that's not right. Is that right?
That's right.
Yeah, that's right. Good job.
No.
Okay.
No,
Oh, no, wait, no,
it's
there was
0.91.
Yeah.
That's
You were so close.
I was really close. This is the number I want to grab. It didn't feel right though. And then I'm going to do the 1.25 on top times 100 to get it into a percent. And that's going to give me 1.03%. All right. Does that help? Does that work? Everybody cool with that? Remembering your stoichiometry? All right. We've got eggshells here. We got calcium carbonate in your eggshells. We're going to react our eggshells with acetic acid from vinegar, and this reaction is going to happen. Looks like they've already balanced it for us. We've got carbon dioxide produced, and this many eggshells that we started out with. What is the percent by mass of the eggshells from calcium carbonate? All right. So I'm going to take my CO2 and I'm going to do what with it? Yep, I'm going to turn it into moles. I'm going to do that by dividing by, which is 44. Good. I took a carbon at 12 and 2 oxygens at 32. 12 plus 32 is 44. Okay, so that's going to give me my moles. See if I can do this right. I ended up with 0.100 moles of CO2. All right, now we could spend time writing out a BCA table, but I notice that I have one of these, and for every one of those, I have one of these. So that means to get this, I would have had to have how many moles of this? The same, because they're in a 1-to-1 ratio. I could take this and go up into the cloud and divide by 1. Divide by 1, and then come back out and multiply by 1. I'm going to end up with the same amount here for moles. Does that make sense? Okay. So if I've got that many moles of CO2, that means that I've got that, I had to start with that many moles of CaCO3. So now I need to get that into grams, because they want percent by mass. So I need to multiply this by grams. Is that not right? Yeah, that's right. Per mole. Moles cancel, and that's going to leave me with grams. So that's going to give me 10.05 grams of CaCO3. Is that my answer? No. They want a percent. So I need to divide this by the grams of the eggshells. Times 100 equals. Oh, I already have that. So 95.15. And you guys need to start getting used to writing your units down on the AP exam. If you have naked numbers, they will mark them wrong, even if you have the right numbers there. If you don't have the units written down, they'll mark it wrong. It is what it is. Yes, sir.
Where'd you get 1054?
This?
Yeah.
That was, oh, it should be 7. Sorry. Yep, just Lippy making a mess again, like usual. Yep, ask those questions because it's probably me making a mistake. I do it all the time. I know. It is who I am. Sorry, y'all. All right. Any other questions on this one before we put 1-4 to bed? All right. The next one's going to be fun if you haven't been in here.
Then once you have to change it, you said.
No, because I was just reading off of my answers. Like I had my answers down. No, I didn't calculate from now. I calculated a year ago. And I checked my answers against the answer key from the person that I got these things from. So, yeah.
Oh, Miss Sophie, do you remember Maddie Ratzel from 2016?
Yeah.
She says hi.
Okay. Tell her hello. All right. Atomic structure and electron configuration. All right. So remember, back in the day, we had quantum numbers. N, L, M, and S. Okay? So N is how far the electron's away. L is what kind of orbital it's in. M is its orientation in space, and S is its spin. Okay? And we can use those quantum numbers to help us figure out the electron configuration. You don't have to do quantum numbers on the AP exam, but if you understand quantum numbers, it makes electron configuration very easy. Right? So again, this is going to correspond to the row on the periodic table. And remember, if you're in the D sublevel, you're going to subtract 1. And if you're in the F, you subtract 2. Then this is the sublevel, what kind of orbital it's in. So S is the first 2 columns. P is the last 6. D is that middle section where your transition metals are. And then F is that bottom section. Okay? All right. So again, we've got different orbitals. Our S orbital is a sphere, which is easy to remember. Our P orbital is like a dumbbell or a peanut. And then you have your D's, and then your F's are even worse. Okay? Each orbital can hold 2 electrons. So the S orbital can only hold 1. You can kind of see how those work. Okay? So here's your different electrons that these can hold. Okay? All right. Electron configuration, there's this guy that you can have, or you can just use your periodic table. This is your orbital diagrams, though. Okay? Coulomb's law also comes into play here. Am I? Yeah, I'm good. Okay. I know, I went too fast. You're okay. Coulomb's law then tells us that the force of the charged particles is proportional to how far they are away from one another. And that's going to come into play when we get into periodic trends next week. I believe it's next week that we get into those.
It's Friday.
Oh, this week?
Yeah.
Okay.
Then we have a quiz next.
Whew. All right. So if you think about magnets, the closer you get to them, the tighter the force is, right? The stronger that force, the further away, the weaker the force. The stronger the magnets are, the stronger the force together. Coulomb's law is the same way. And what we're doing, looking there, is the force of the protons, the positive charges, and your electrons, the negative charges. So the further those electrons are away from the nucleus, the easier it is to remove them. All right. Remember, for electron configuration, your off-bow principle, which means that you have to fill in a certain order, and you use your periodic table to help you with that. Hund's rule, each sublevel should have at least 1 electrons before they double up. And then no 2 electrons can have the same spin. All right.
Wait, I like this one.
Okay.
I like labeling.
So when we do this, remember your helium comes from over there. It kind of lives here when we're doing electron configuration. And you follow in numeric order. So this is your 1s. This is your 2s. After number 4 comes 5, so we pop over here. This is your 2p, 3s, a 3p, 4s. And remember, when you get into this D level, you have to subtract 1. So this is 3d. This is 4p. And you just keep following a numeric sequence until you get to where you're going. So here, this is the electron configuration for what element? Lithium. Now, how did he figure that out? What you do is you look at these numbers. These numbers will tell you how many electrons there are. So 2 plus 1 is 3. And if you find 3 on the periodic table, it's lithium. Here, 2 plus 2 is 4, plus 3 is 7 total. So that is nitrogen. So that's all you have to do is just add those numbers up, and they tell you what element it is. Okay? They're also going to be able to look here, tell you what row from the periodic table it's in. It's also going to be able to tell you what orbital that last electron's in. So this is a p orbital. That means that it's going to be a peanut-shaped orbital. All right, orbital diagrams then. Remember, that's where we use the up and down arrows to indicate what's going on. And I'll show you how to do one of those in a couple minutes. All right, here is an orbital diagram. If you want to know what element this is, you count the number of arrows. 2, 4, 5, 6, 7. This is nitrogen then.
Do we get the Coulomb? Oh, wait. Oh, wait. They're not. Okay.
Here, this one is incorrect because we can't have 2 electrons in here until we have 1 in each spot. So here, this is correct. This is not. All right. We also have what's called noble gas electron configuration. Your noble gases are your last column on the periodic table. So when we do these, you go back in your electron configuration and you find where you had your last noble gas. Right here was your last noble gas, and that guy would have been argon. So you write argon. Most people do not write this number here, though. Don't do that. So write argon, and then 4s2 would be your last 2 electrons. So this is calcium. All right, unless specifically stated to write the complete electron configuration, the noble gas configuration is always acceptable on the AP exam.
Cool.
If they use the word complete, though, you better write the whole thing out.
So true.
Okay, all right, they want us to write the ground state electron configuration for arsenic. So I'm going to go back to this periodic table here so that we're all on the same page. Here is arsenic. Okay, so I'm first going to do the complete one just to show you how to do a complete. Remember, for this, my helium would actually be here. And I always start back. It's like a chutes and ladders game. We always start at 1. So we start here. This is my 1, because remember, these are 3, 4, 5, 6, 7. These are our period numbers. So this is 1. This whole thing right here is my S block. And I'm going to arsenic, so I need both of those electrons to make that work. So 1s2. This was number 2, so after number 2 comes 3. So I'm going to go back down here. I'm going to grab these 2. This is my 2 for my period. This is my S block, and I have 2 electrons there. After number 4 comes 5. So I come over here. I'm still in the second period. This is my P block, so I'm going to write down a P here. I need to go to arsenic. I need all 6, 1, 2, 3, 4, 5, 6 of these electrons. After 10 comes 11, so I go down here. This is my 3s, third period s block. I grab both of those electrons. After 12 comes 13. I need all 6 of these. This is my third period p block. Remember, this is your p block here. So 3p, and I need all 6 of them. After 18 comes 19. So I'm going to go down here and grab these 2. This is my fourth period. This is my s block, and I need both electrons. 4s2. Now, when I come here to get my next section, this is my D block. When I get into the D block, I have to subtract 1 from the period. So this becomes 3D, and I need all 10 of these elements to get me to here. Over here then, we're back into the P block, so I'm going to write the period down. It's my P block, but now I don't need all 6. I just need the first 3. So this is my electron configuration, my complete electron configuration for arsenic. Now, they didn't ask for a complete one, so I could write down my noble gas one. If I'm doing a noble gas, I'm going to take this back until I come to my previous noble gas, which is right here. This is my previous noble gas. I'm going to find where that is here. So all of this stuff here gets me up to argon. So I'm going to get rid of all of that.
Did you order little bottles of hydrochloric and acetic? Okay.
And I'm going to write argon there. And I can verify that I have the right configuration by taking this 18, adding 2 plus 10. So that takes me to what? 18 plus 10 is 28, plus 2 is 30, plus 3 is 33. I've got the right electron configuration written down then. All right, I'm not going to get to 1-6 today, so you're doing 1-4 and 1-5 for homework tonight. Yeah, ions then. Remember what happens with ions. This is is it 2 plus?
Yeah.
Is it Ca? Is this one? Okay. So that you're going to lose 2 electrons out of it because it's a 2 plus. It would have lost 2 negatives. So it's going to have the electron configuration then of argon. You cannot. You can do neon, and then you go down here, neon 3s2 3p6.
So then when it's like S negative, it would be oxygen instead?
What?
There's an F negative. Or
F minus 1?
no, it's just a negative.
It's just a negative. It's just that one, right?
Oh, so that means it's as an electron.
Yeah, so it'd be neon.
So it's going to be this, yeah, it's neon's configuration. Yep.